Given an array of non-negative heights for vertical lines on the x-axis. Pick any two distinct lines, with the segment between them on the ground. They form a container. Water height is the shorter line, width is the index gap, so area is width times that minimum height. Return the largest area you can get. Constraints: keep n in a safe range and heights within 0 to 10,000. Example 1, heights 186254837. The best pair is index 1 height 8 with index 8 height 7, width 7, water level 7, so 7 times 7 equals 49. That is the maximum output. To understand this problem, we first need to know how water behaves. The amount of water a container can hold is limited by the shorter line. Even if one side is a skyscraper, if the other side is a puddle, the water will spill out at the lower level. So the area is simply the distance between the lines multiplied by the height of the shorter one. The simplest way to solve this is to check every possible pair of lines. But if we have thousands of lines, checking every combination takes way too long, order n squared. We need a strategy to skip the pairs that do not matter. Let's start with the widest possible container by putting our pointers at the very ends of the array. From here, any move we make will shrink the width. To make up for losing width, we must find a taller line. Here is the key: the shorter line is the bottleneck. Moving the taller line inward is pointless because the shorter line still caps the height, and the width is smaller. But if we move the shorter line, we might find a much taller wall that makes up for the lost width. So our strategy is simple: always move the pointer on the shorter line. We keep shrinking the window and hunting for higher peaks, until the pointers meet. By always moving the shorter line, we only spend time on containers that can still beat our record. We find the best container in a single linear pass. We put the left pointer on the left end and the right pointer on the right end. The left wall has height 1, the right wall height 7. We keep a running best area, starting at 0. The width between pointers is 8, and the water level is the minimum of 1 and 7, which is 1. 8 times 1 is 8. We record 8 as our current best. 1 is shorter than 7, so the left side limits the water. We slide the left pointer inward looking for a taller wall. Now the width is 7 and both walls reach 7 tall, so 7 times 7 is 49. That beats 8, so we update our best to 49. Between 8 and 7, 7 is shorter. We move the right pointer one step toward the center. Width 6 with minimum height 3 gives area 18. That does not beat 49, so the best stays 49. 3 is shorter than 8, so we move the right pointer again. With width 5 and height 8 on both sides, the area is 40. Our record of 49 still holds. When both sides show height 8, we advance the left pointer and the window keeps shrinking. None of the remaining windows beat 49. When the two pointers meet, every promising container has been considered. The answer is 49. Time is order n, each pointer walks inward at most n steps in total, and each iteration does constant work. Space is order 1 beyond the input, 2 indices plus the running maximum, no extra arrays. Define max area as a function of the height array. Set L to index 0 on the left. Set R to the last index on the right. Initialize the best answer to 0. Loop while L stays strictly less than R. Compute the current width as R minus L. Water height is the minimum of the two wall heights at L and R. Update the answer with the maximum of the old answer and width times height. If the left height is less than or equal to the right height, we advance the left pointer, ties pick L. Increment L by 1. Otherwise the right wall is strictly taller, so move the right pointer inward. Decrement R by 1. Return the accumulated best area.